In previous videos, we had been looking at solving differential equations of this form ay double prime plus by prime plus cy equal to 0. And we discussed how it boils down to solving this quadratic equation, ar squared plus br plus c equal to 0. We stated that if the roots of this, the solutions, were real and distinct, then our solution was of the form c1 e to the r1t plus c2 e to the r2t. And if we had repeated roots, it was of the form y equal to c1 e to the rt plus c2 t e to the rt. So now let's look at what happens when we have complex roots. If our roots are of the form alpha plus or minus beta I, then we know our solution looks like c1 e to the alpha plus I beta t plus c2 e to the alpha minus I beta t. So this just goes back to the fact that these are two distinct roots, so we want them as the exponents to the e. We can break these e's up into e to the alpha t times e to the I beta t, and then I went ahead and factored out the e to the alpha t. Using Euler's identity, I can rewrite these exponents, these e to the I beta t, as cosine beta t plus I sine beta t. The next thing I'm going to do is rewrite these cosine minus beta t and sine minus beta t. Cosine of minus beta t is the same as cosine beta t, and sine of minus beta t is the same as minus sine beta t. I'm then going to regroup things. I have two cosines, a c1 cosine and a c2 cosine beta t, and I have two sines, a c1 and a minus c2, so I just went ahead and rewrote those. And just like when we talked about systems, you can plug this in to the original differential equation and show that the I here is unnecessary. So I'm going to rewrite this as e to the alpha t times c3 cosine beta t, since c1 plus c2 is still a constant, plus c4, because once again, c1 minus c2 is another constant, sine beta t. And this is the form for our differential equation whenever we have complex solutions. Let's look at an example. We need to start by solving our auxiliary equation, or our characteristic equation, r squared plus 2r plus 2 equal to 0. Using the quadratic formula, we have negative b plus or minus the square root of b squared minus 4 times a times c. So that will be 4 times 1 times 2, which is 8. All over 2 times 1, which is 2. So this is negative 2 plus or minus the root of minus 4 over 2. We know the root of negative 4 is going to be 2i. So I have negative 2 plus or minus 2i, which is the same thing as negative 1 plus or minus I. So in this case, alpha is minus 1 and beta is 1. So when we write the solution, we have e to the alpha t times a constant times cosine beta t plus another constant times sine beta t. We do want to solve with our differential equations here. So I'm going to need the derivative as well. We have the derivative of the first times the second plus the first times the derivative of the second, which will be minus c1 sine t plus c2 cosine t. Now we know, using our first equation, this is equal to 0 whenever we stick in 0. So that'll be e to the 0, which is 1, c1 times 1 plus c2 times 0. Using this one, I know the derivative is equal to 2 whenever t is equal to 0, so this will be minus 1 times c1 plus 0 plus 1 times 0 plus c2. So that gives me 2 is equal to c2, since we know c1 is equal to 0. So my solution would be 2 e to the minus t sine t. Let's do another one. This time I don't have initial conditions and I just want to solve this equation here. The quadratic formula says minus b, so negative 2, plus or minus the square root of b squared, which will be 4, minus 4 times a times c. So that's 4 times 1 times 4, which will be 16, all over 2 times a, which is 1. This gives me negative 2 plus or minus the square root of negative 12 over 2. This is the same thing as plus or minus, or negative 2 plus or minus 2i root 3 once we simplify that square root, all over 2. So negative 1 plus or minus I root 3. In this case, alpha is negative 1 and beta is the square root of 3. So my solution would be e to the alpha t, so e to the minus t, times c1 cosine beta t, so t times root 3, plus c2 sine beta t, so c2 sine t root 3. And now I have my general solution.